Okay, so we said hydrogen must be present. He must be attached to fluorine, oxygen, or nitrogen. And the third is that these elements need to have at least one lone pair in the molecule. In other words, if the fluorine is attached to the hydrogen, but also is attached somehow to another element through beta bonds or something like that, because it has already completed the octet, then this special dipole-dipole bond cannot be formed. So the oxygen, nitrogen, or fluorine have at least one lone pair. Why is that? Because this special bond is going to be only between the lone pairs of one molecule, let's say that this is the molecule, yes, and another molecule that has a hydrogen. So this lone pair here is going to be attracted to the hydrogen, what we call a hydrogen bond. And that is the second type of intermolecular forces. Okay? So far so good? Now, how do we represent that? Or how do we do it? Exactly the same as always. They say hydrogen fluoride and another one of hydrogen fluoride. This one is a dipole, so the negative zone of the fluorine is going to be attracted to, actually it's not the negative zone, but the electrons are going to be there. The lone pairs, actually, let me put the black thing. The lone pairs 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. This lone pair, let's say, is attached to this hydrogen here. Is that clear? Now, this bond, the hydrogen bond, is much stronger than the dipole-dipole. That results in a higher melting and boiling point. So when you see, for example, the melting and boiling point of the elements in the group 7, you're going to see the hydrogen fluoride up to here, then you are going to have the hydrogen chloride, then you are going to have the hydrogen fluoride, this is hydrogen fluoride, this is hydrogen chloride, this is hydrogen bromide, this is hydrogen iodide, okay? So, but this one is much higher than all these three. Why is that? In this one, the only forces that I need to overcome to boil it is the dipole-dipole. In this one, it's even worse, or it requires more energy, because it's not only dipole-dipole, it's hydrogen bond that is present. Yes? Same happens when we have water. We are going to have H, H, and O, and the lone pairs are going to be attracted. I'm going to do it bigger. They are going to be attracted somehow of the hydrogen of another oxygen. Yes? And this one also is going to be attached to a hydrogen that is present in another oxygen, in another water molecule. And they are going to form groups. Okay? This hydrogen bond is super important, not only in chemistry, but also in biology. Because when you have the double helix, and I don't know how to draw the double helix, okay? So I'm going to do my best. So when you have the double helix for the they don't touch each other. Let me erase this. Now that I have a very good picture of this, I can explain you that in the case of these here are covalent bonds in between the atoms that are in all the things, but these here are hydrogen bonds. All these, so the double helix is all covalent bonds in the helix, yes, but in between the two helix, these are that are here, all these are hydrogen bonds. So that is how important it is. Okay, now the hydrogen bonds also are going to be the responsible for the ice to float in water, because the hydrogen bonds makes the structure to be a little bit farther away than they are in the liquid, because in the liquid they are closer to each other. So the molecules of water are like this in random places. I'm sorry, but when they are in the ice, they are going to form structures. Okay, so they are a little bit farther away from each other, and that's why the ice floats in water. Yes? The same thing they can ask you about the boiling and melting point of water. Most of it, the boiling point. If you take the group 6, in the group 6, you have the first one is going to be water, yes? So water is going to be at 100 Celsius. But then you have the hydrogen sulfide, which is H2S, is going to be much lower. And then you have H2 telluride, yes, hydrogen telluride, and then the other ones, but selenium, and then tellurium, yes? Okay, so this one is much higher than the other ones. Why is that? Hydrogen bond. Good? Now, the last one that we are going to see is the one that happens when we are talking about non-polar molecules. Because so far, we talk about polar molecules, yes? Okay, so non-polar. And you're going to say, how can they interact? Well, the thing is this, the electrons move all the time. And that is so important. Why is that? Let's say that I have a chlorine molecule, yes? So I have my chlorine molecule attached to a chlorine atom attached to a chlorine atom, and the electrons are evenly distributed all over the place. Do we have a dipole there? Do we have a dipole? No, because the electrons are evenly distributed, we said, because the electronegativities of the chlorine on the left and the chlorine on the right are exactly the same. Is that okay? But the thing is that the electrons are moving all the time. So for fractions of a time, I don't know if fractions of seconds, maybe, okay, some of these electrons that are evenly distributed are going to begin moving or stand in near to this, let's say, chlorine a little bit more. What happens is going to form what we call the temporary dipole. And that is temporary because eventually the electrons are going to go around the other chlorine again, and this is going to be 99% of the time a non-polar molecule. But since the electrons are moving, these electrons can be concentrated in one chlorine. They